purpose of this video is to teach what vectors are and how we use them primarily for 3D graphics and video game programming. A knowledge of vectors is prerequisite to understanding motion and shader programming in most graphics programming. What vectors are not? Standard template library has basically classes that are called vectors that are really more like dynamic arrays. That really has nothing to do with vectors that we're going to be discussing here, and it could be a source of confusion if you're doing C++ programming. If you're doing OpenGL or DirectX or anything where you're using vectors in C++, having STL call their dynamic arrays vectors just gets really confusing if you're starting out and you're not already comfortable with that. It's not the same thing at all. Also, the Center for Disease Control, for example, calls something that spreads disease a vector. It's a source that spreads a disease. That's not what this is either. What vectors are? You should probably think of vectors as arrows. When you're imagining them in your mind, you probably want to think, just imagine an arrow in 3D space or 2D space if we're working in 2D. They're basically a representation of a direction and an amount that are permanently tied together as one quantity. It's an amount and a direction that are inseparable. So this is the vector mantra. You want to keep repeating this until it's burned into your brain. Vectors are nothing other than a direction and an amount that are permanently tied together. It's important to think of vectors as being a direction and an amount, and anything that doesn't meet that definition is not a vector, because otherwise you're going to get really confused. Is an STL vector that we just talked about, is that a vector? Well, no, it's not a direction and an amount. It's a dynamic array. It's totally unrelated and doesn't have anything to do with this. But something like a position stored as a vector, is that really a vector? And we'll cover that, but I want to make it clear that the position of a vector is completely irrelevant. It doesn't have anything to do with a position. A vector is, you can think of it as an arrow that points in a given direction, and its length, the length of the arrow, is its amount. And so it has two positions. It has a position of the arrow head and the arrow tail. But as long as the arrow points in the same direction and as long as it has the same length, that's all we care about. We don't care where the arrow is actually at. Its position is totally irrelevant. And another thing that people want to do when they're starting out is use vectors as tuples, like quintuplet, quadruplet. Basically, when you store a group of numbers together, that's basically a tuple. And so they'll try to use these vectors because a vector stores the arrowhead's position. So in 3D that'd be 3 floating point values, x, y, and z, and they'll try to use those 3 values to tie 3 numbers together that have nothing to do with vectors. One that I see fairly commonly is pitch, yaw, and roll, which don't really have anything to do with vectors directly, but somebody will shove the 3 values into a vector, and that's not really what a vector is. So here's what a vector really is. Think of them as arrows. The arrow's direction from its tail to its head represents the direction of the vector, and then the arrow's length is its amount. So whatever direction the arrow points, that's the direction of the vector, and whatever length it is, that's its amount. It's also called a magnitude of the vector sometimes. And really, this is how you should always think of vectors. I can't think of one single example where you have an actual real vector where you can't think of it as an arrow. And using the arrows in your head will make it, I think, a little bit more clear in trying to visualize it and trying to see what we're talking about. Imagining it as arrows, I think, will make that a little bit more clear. So why do we use vectors? Sometimes a quantity becomes meaningless if you separate the direction from the amount. It has no meaning whatsoever if you don't have both the direction and the amount. For example, what does it mean to move 3 feet? How do you move 3 feet? Should you move 3 feet forward? Should you move 3 feet back? Should you jump 3 foot into the air? Or should you go find some other person so that you have 3 feet that you can wiggle? I mean, what does it really mean to move 3 feet? It doesn't really mean anything unless you have the direction tied to that. In fact, it can mean the exact opposite. If somebody wants you to move 3 feet back and they say move 3 feet and you move 3 feet forward, they're moving further away from their intended goal. Now you have to move 6 feet back in order to get to the same spot. You're not only not doing what you needed to do, you're actually making things worse, because the direction and the amount have to work together to reach the end goal. And so here we're talking about moving 3 feet. You've got the amount there and we don't have a direction. What about a direction where you don't have an amount? What does it mean to move west? You've got the direction west, but how far west? When can you stop? And how are you going to know that you've arrived where you're supposed to go? Should you go 12 feet west? Should you go 28 kilometers west, 18 inches west, 46 light years west? How far west are we going here? Should you maybe put on a cowboy hat and move to Montana? Where exactly are we going? So you really don't have enough information there if you simply say go west. You really need something specific where you have both an amount and a direction that are tied together. And if you break the two apart, it can mess up the whole situation. Like the forward and backwards situation, it's not good enough to just say move 3 feet. It's not good enough to just say west. And if you break them apart, if it were 3 foot west and then 2 foot east, 3 foot west and 2 foot east is not the same thing as 2 foot west and 3 foot east. If you switch the numbers between east and west, or especially if it's so many feet north and so many feet east, or meters or whatever unit, it's not the same thing. You can't break them apart. The number, the amount, the amount must stay tied to the direction. And that's why we use vectors in the real world, is because there are times where you can't separate them. They have to be treated as one quantity. And any time we have that is an appropriate place to use a vector. So vectors can be used for a lot of different things. We're mostly going to use them for movement and describing directions. Maybe occasionally describing distances and so forth, but there's a lot of different ways you can use them in physics or in game programming, or any way that you can imagine where you need an amount that's tied to a direction and the two are basically inseparable. That would be an appropriate place to use a vector. If you have a direction and amount tied together, you know exactly where to go. So here we got the arrow that's pointing, I want you to go right here. It shows you the exact distance. It shows you the exact direction. You cannot separate the direction and the amount or it loses its meaning. Moving 3 meters to the right is completely different than moving 3 meters to the left. Moving 6.5 miles up is completely different from moving 6.5 miles down, or even 6.5 miles east. And notice I'm using all these different units: miles, meters, kilometers, parsecs, light years, micrometers, whatever. the unit doesn't really matter. We can use vectors with any type of unit. The only important thing is you probably want to be consistent about using one unit. In game programming, we primarily use meters for just about everything when it comes to distances and speed and things like that. We strongly prefer the metric system for a lot of reasons, which basically boils down to it's far superior to the English system. But one unit in the game world, we could set that to be any unit, any type of unit that we want it to be, miles or inches or kilometers or whatever, but it's just kind of a standard in the game industry that 1 unit equals 1 meter. It doesn't have to be that way. It's just what everybody has chosen as the standard, and almost always you'll see that being used. But here I'm showing that vectors could be used with any type of unit. 4 yards is completely different from moving east, or moving east 4 yards is completely different than moving east 10 yards. And so on and so forth. I think you kind of get the point. You just cannot separate the direction and the amount, or it can change the meaning entirely. We can use vectors for anything where we need to represent an amount and a direction permanently tied together. If it makes sense to tie those two things together, you can use a vector. Often we use vectors to represent forces in physics, in real-world physics as well as game physics. We use vectors a lot because forces often need to be tied to a direction. If you push with 3 pounds of force north, that's totally different than pushing 3 pounds of force, or with 3 pounds of force, south. In fact, the two will cancel each other out. The direction that you push in is just as important as how hard you push. In this example drawing, maybe you could have a dog that's pulling with 12 pounds of force towards 15 degrees east. You got the direction 15 degrees east, and you got the amount of force 12 pounds. How are vectors used? Vectors are used in many ways in computer games. More than anything, you'll see them when you're programming shaders, like high-level shader language in DirectX or XNA or Monogame, or GLSL for OpenGL, or CG in Unity, for example. Although Unity, I think, at least in some places, will use HLSL and GLSL, I believe. But when you get into shader programming, you're almost immediately going to get into vectors, especially normals, and need to understand basically what those vectors are, how, what a normal is and how it works. In shaders, they're used for things like determining which direction a surface is facing and whether a light is facing that surface. So we use vectors, especially normals, in determining how to simulate lighting a lot of times. If you get into doing shaders with post-processing effects, basically the way a post-processing effect works is you draw the entire image, you draw the whole screen, and then you take that final image and then you process that. Maybe you turn it to black and white instead of color, but it's applied to the final image. You're not using that type of shader, is not used to draw the original image. You draw the entire image and then you take the final image and then further process that. That's post-processing. When you program shaders to do that post-processing, and those tend to not use vectors, so they might be a good way to get into shaders without really getting into shaders, because when you get into the original shaders, even the most simple shaders like Blend Phong shaders are going to heavily use vectors, especially normals, and it's kind of one of the advantages of something like Unity, where you can kind of avoid the subject of shaders and you can avoid getting deep into vectors, because it kind of obfuscates or hides a lot of the details from you. But when you go into like DirectX programming or OpenGL programming, especially with the newer versions like DX11 or OpenGL 4, you have to program all your shaders. You can't do anything without programming your own basic shader. So one of the first things you need to do is something like a blend Phong shader, where it allows you to draw stuff to the screen. And so from day one, from the very beginning, you are forced to have a solid understanding of vectors, especially vector normals, and how they work and why they work. And it's really kind of a hurdle for a beginner, especially if you don't have a lot of experience in some other environment. You're going directly into DirectX with HLSL, to have to program your first shader starting on day one just so you can see anything appear on the screen, even the most simple things. It's a pretty daunting task, and it throws you into the world of vectors. It just kind of throws you off into the deep end of the pool, And so I think if you understand vectors here, you'll be much more prepared to get into writing shaders, whether it's in DirectX or OpenGL or really any other environment that you write shaders in. But most frameworks these days, like Unity, for example, you don't have to get into shaders until you're ready. The newer versions of OpenGL and DirectX, you've got no choice. You've got to get into shaders to do even the first thing that you do. Nothing can be done without getting into shaders. And so if you're going to do that, then if you're going to go into OpenGL or DirectX, you've got to understand this vector stuff pretty solid. I mean, you don't need to understand how to do vector math, but you do need to understand what vector math means. You need to understand why you would want to add two vectors together, or why you'd want to subtract one vector from another, that sort of thing. And you need to understand what a normalized vector is and what it represents. So continue on with the slide. In shaders, they're used for things like determining which direction a surface is facing and whether a light is facing that surface. We store positions in vectors, even though thinking of vectors as positions just makes the subject more confusing. We'll get into that later, but at this point I want you to think of vectors as not having any sort of position. It's actually two positions that are relative to one another, which allows us to calculate a direction and an amount. But the position doesn't matter. What matters is the direction and the amount. What direction does the arrow point and how long is it? Where the arrow actually is generally irrelevant. And I want you to be thinking of that, or thinking in that way at this point. They can be used to describe movement. They're used in physics for things like velocity, acceleration, and forces, both in the real world and in our gaming world, because when we start trying to describe movements, if we want them to look realistic or act realistic, we're probably going to have to get into some basic real-world physics and program that real-world physics into our simulation, which means that we'll be needing vectors in order to program that real-world physics. Okay, so let's get into some actual vector math and look at how we actually do math with vectors. What does it mean when we're doing math with vectors? How's it done? But realize that I'm only showing you this so that you'll understand how to properly use the vectors. This is very much like using a calculator. You don't necessarily need to know how to do long division if you know how to do division on a calculator, but you still need to know why you would want to do division in the first place and what the answer actually means. What does your input mean? What does your output mean? That you still have to know. Actually, how to carry out the division and actually do the math, you don't need to know that if you've got a calculator handy. It's the same situation here with vectors and matrices, that the framework you're working in, the API, whatever it is that you're working with, it's going to know how to do the math for you. You don't need to know how to do the math because it's already built in. If you want to add two vectors together, in some environments it actually knows the addition operator, and you can have two objects, vector A and vector B, and you can just say vector C equals vector A plus vector B, and actually use an actual plus sign, and it actually knows how to add two vectors together. In other environments, there may be some method or function or something where you say vector add, and then the two parameters are vector A and vector B, and the result of the method that it returns is vector C. But regardless of how it carries it out, pretty much all of this stuff mathematically is going to be done for you. So you're not really trying to learn how to do the math here. You're trying to learn why we're doing the math. What is, when do we need to do the math? Why are we doing the math? What does the result mean when I get a result back? So first of all, let's start with what do vectors look like. On the left side here, we've got Cartesian coordinate plane. Hopefully you're familiar with that from school, where you've got an XY axis or axes, and you're graphing on it. I had to draw these myself, and I didn't have anything handy that would allow me to do tick marks. Normally you'll see tick marks on the graph, or you'll have graphing paper where you've got squares or whatever, and I don't really have that here and didn't have an easy way to draw it. So just kind of imagine that my graphs are actually proportional. I wasn't extremely rigorous with the ratios, the aspect ratios, and getting everything geometrically perfectly correct, or even mathematically perfectly correct. In some cases I rounded, and there may be some rounding errors and whatnot, but I'm really trying to show the concept here rather than the specifics. And so for example, this vector, I've got the red arrow, which is our vector, and the origin is always, or the tail is always at the origin, which in this case in 2D is 0, 0, x equals 0, y equals 0. And the head is at 4, -2, or x equals 4 and y equals -2. And I drew dotted lines to kind of make a square here, where you've got the blue dotted line, which has a length of 4, and the black dotted line, which has a length of -2. And you can see that it kind of forms a square there. Remember the mantra: a vector is nothing more than a direction tied to an amount. That means position is entirely irrelevant. Vectors always have their tail at the origin, or all the vectors that we're ever going to use in game programming do anyway. Theoretically, the vector can be anywhere, which means it doesn't have to have its tail at the origin. But then the math becomes more complex, and you still end up basically having to bring it back to the origin to do math on it anyway. And it's just easier to store just the position of the head. If you think of storage space in the computer, if it takes 1 byte to store each number, then the vector head is 2 bytes. If you stored both positions, that'd be 4 bytes. By zeroing it out and just assuming that the tail will always be at the origin, you're getting rid of half the vector. You're getting rid of, in that case, 2 bytes. If it's 8 bytes, or if it's 16 bytes in total for head and tail, then you're saving half of it, which would reduce 16 bytes to 8 bytes for every single vector that you have. There's a massive storage space here in terms of computer memory and memory in the CPU and memory on disk, and it's just far, far, far more efficient to only store the position of the head. And there really is no reason whatsoever at all to ever have the tail position away from the origin, because going back to the mantra, a vector is nothing more than a direction tied to an amount. So direction, amount, that's all that matters. Position is not part of that. That's totally irrelevant. And so there's just no reason ever to have the tail at any position other than the origin, and it's just far more efficient to only store the head position. However, vectors are 2 points, even though we only store one of the 2 points. Keep that in mind. It's the second point, the tail, the point of the tail, is always assumed to be at the origin. So you can't really have an arrow unless you got 2 points. And even though we don't specifically say what the second point is, just know that that second point is always the origin. Because of that, we only need to keep track of where the arrowhead is at. That means the direction of the arrow can always be determined by the direction from the origin to the point of the arrowhead. This also simplifies the math because the tail is already zeroed out, which if you were going to walk through the math and you had the vectors positioned someplace else, a lot of times you would probably have to still basically move it back to the origin to do the math. What do 3D vectors look like? Okay, so here is an example of 3D vector, the red arrow, and I've drawn first of all on the 3D Cartesian coordinate system. We have 3 axes now, x, y, and z, or x, y, and z, depending on where you live. And we have what they call right-handed coordinate system and a left-handed coordinate system. Basically, since we already had our x and y plane, and if we're going to add a z-axis, it's kind of arbitrary whether moving forward is positive z or whether moving forward is negative z. There is no standard for that. There is no universal truth that dictates that. Basically, we just decide, what do you want it to be? And it changes from environment to environment. Sometimes the change gets very annoying, like Blender, for example, switches all the axes completely around, and so when you model something in Blender and you export it into your environment, 9 times out of 10 it's going to be oriented wrong because the axes were totally different in Blender than they are in whatever environment you're working in. But there's no universal truth that dictates it, and so everybody gets to basically decide on their own, and there are some standards between some environments, but for the most part every environment could possibly be different. So for this discussion, we're just going to say z forward equals positive z and z backwards is negative z. In this case, we've got a 3D vector, which I've said x equals 4, y equals negative 2, and z equals negative 4. And that 4, negative 2, negative 4 is the position of the head of the vector. I will say this now that these coordinates can be fractional, like 4.5, negative 2.638, negative 4.00005, or whatever. I'm using integers here, just kind of rounded numbers just for simplicity, but in reality when you're working with them most of the time they'll be floating point numbers that are real numbers, numbers that have decimal places. So just understand that. Instead of only an x and y value, we add a z value to represent depth. The direction of the axes change from environment to environment, but the principle is the same. Again, the tail of the arrow is always at the origin where x, y, and z are all zeroed out. The distance between the origin and the point stored is the amount or magnitude or length of the vector. That all has the same meaning. Whether you say the amount of the vector, the magnitude of the vector, the length of the vector, it's the same. It's the length of the arrow. And the length of the arrow represents an amount of something. It could be an amount of anything depending on what you want it to be an amount of. And magnitude and length basically have the same meaning here. So those 3 terms are basically interchangeable. They all basically mean the same thing, the length of the vector, the length of our arrow. And I've drawn this 3D box in the drawing where all the blue lines are 4 in length and all the black lines are negative 2 in length, and all the green lines are negative 4 in length. And you can see that the vector, that was largely to kind of give the illusion that the vector is 3D, even though I'm actually drawing on a 2D surface. But it also illustrates that a vector can form the diagonal of a three-dimensional box. And in game programming, you'll actually see that on occasion where they represent a box as a vector, and the vector basically represents the diagonal of the box. If you combine that with a position, the box can be positioned anywhere in the world. So the vector represents the dimensions of the box, and the position allows you to reposition that box anywhere in the world. Here in this drawing, showing that the length of that vector is its amount. The amount stored in the vector is represented by the length of the vector, the length of the arrow. The length is also sometimes called the magnitude of the vector. It doesn't matter what type of amount it is. It can be an amount of inches, meters, an amount of temperature, an amount of weight. It can be an amount of basically anything, as long as the vector represents something, and it represents the direction of something and the amount of something. That could be any something. All that it really has to be is something that the amount and the direction need to be tied together. And when you're working with vectors, you probably want them to work together. For example, if the vector amount is meters and you try to combine that with another vector that's in inches, that doesn't make sense until you convert the inches to meters, really. So, how do we calculate the amount of the vector? How do we calculate the length of the vector? The answer is the 3D Pythagorean theorem, which, if you're new to vectors, you're probably new to the 3D Pythagorean theorem as well. You may be new to the Pythagorean theorem in general. Real quick, the Pythagorean theorem is a mathematical idea that was supposedly developed by a guy, I think, who was named Pythagoras, who formed a religious cult in the Greek Empire, or whatever you call the Greek times. This Pythagoras cult was basically trying to use mathematics to understand the universe. They saw mathematics basically as magic. And if you can imagine people from 400 BC being thrown in today's modern world, they probably would think all the things around us are magic. To them, math was magic, and they were really trying to understand the magic of the universe and how the magic of the universe worked. And so apparently there were some very religious aspects of the Pythagoras cult, but one of the things that they discovered a lot of truths about mathematics, and specifically triangles, and one of them was the Pythagorean theorem, that the hypotenuse of a triangle or the hypotenuse squared of a triangle is equal to the sums of the two squares of the two other sides of the triangle. In plain English, the hypotenuse is the side of the triangle that's opposite the right angle. The right angle is an angle of 90 degrees. So the hypotenuse is the side of the triangle that's exact opposite side from the 90 degree angle. And then the A side or the B side are the two other sides, and it doesn't really matter which one's assigned to A and which is B. So hopefully you have some exposure to the Pythagorean theorem from school. Again, the Pythagorean theorem is c squared equals a squared plus b squared, where a and b are the two sides and c is the hypotenuse side. So if you have two of the sides, you can calculate the length of the other side. In this case, in 2D, we would have the two sides and we'd be trying to calculate the hypotenuse. So here's how the 3D Pythagorean theorem comes into play. Basically, if you imagine this problem, and I got the same problem on a college test once. the test question was basically, you have a box, a 3D box, and what is the length of the diagonal between the two opposite corners of the 3D box? It was essentially this exact problem right here. And I'm looking at it, and I didn't know the 3D Pythagorean theorem. I didn't know exactly how to solve it, but I took logic to it. And I noticed that if you reduce this down to a 2D plane, the 2D Pythagorean theorem applies. So if you imagine the bottom of the box is on the xz plane, if you cast the shadow of our vector onto that, it would form a right triangle between the two sides being z and x, and then it would form a right triangle where the shadow would have the length of the hypotenuse. So we can calculate, using the 2D Pythagorean theorem, we can calculate the length of that shadow. And all that's horizontal. Now if you imagine a second right triangle forming using the shadow and the y of -2 and our vector, once we have the length of that shadow and we have the length of the other side, which is -2, we can use the 2D Pythagorean theorem to calculate the length of our vector. And that's basically, if you really get down to it, how the 3D Pythagorean theorem works. We've reduced it down to a more simplified formula, so you can go directly into doing it, but basically if you took the math I just described and reduced it, you'd get the 3D Pythagorean theorem. So in 3D, to calculate the length of the 3D hypotenuse, you have three sides, and you're basically trying to find the hypotenuse. So if we said the hypotenuse is c squared, then, or the square of the hypotenuse, and that equals the first side times, or the first side squared plus the second side squared plus the third side squared. We've already used a and b. We could use d. We've already used c, so we can't use c really. I mean, you could do it any way you want, I suppose, but we've already used c, and so we could assign it d. Or you could just make it more simple and instead of using a and b, start using x, y, and z. And c squared is the length of our vector. It's the length of our hypotenuse. So the hypotenuse squared equals the x side squared plus the y side squared plus the z side squared. And of course, if you know algebra, you know that we really want not the hypotenuse squared, but the actual hypotenuse. And if you square both sides of the equation, that'll remove the square from the hypotenuse, and you'll get the hypotenuse, or c, equals the square root of the quantity x squared plus y squared plus z squared. So the amount of our vector, or the length of our vector, equals the square root of x squared plus y squared plus z squared. And on the left side, I took our actual vector for -2, -4, and plugged in the values and calculated the length of our vector is 6. So that's how you calculate the length of a 3D vector. And again, you really don't need to know how to do this math. You don't really need the 3D Pythagorean theorem, because your API or framework or whatever you're using is going to know how to calculate a vector length. It'll probably be some method or function called length, and you'll just say, give me the length of this vector, and it'll return 6. And you don't actually have to know how the math works, as long as you know that it's calculating the length of a vector. Controlling where vectors point. So now we know how to determine what the length of a vector is. It's probably pretty rare that you actually need to know where a vector points. Extremely rare. I can't think of any time where it's helpful to know where a vector points. But you probably do want to control where the vector points. You want to set where the vector points. We're still using the same vector for -2, -4. You rarely, if ever, need to know exactly where a vector points. This is generally difficult for most beginning game programmers to deal with. They want to micromanage everything, and they want to know exactly where that vector points, and it just doesn't matter as long as it points where it's supposed to point. And if you do the math right, it'll always point where it's supposed to point. The vector stores the direction. The programmer doesn't need to know what direction that is beyond the position of the vector's head. Beyond the fact that it's pointing where it's supposed to point, you don't need to know where it points. Even if we broke it down into degrees, would that mean anything to you beyond merely looking at which quadrant the vector is in? I mean, how do I even tell you where it points? There's, if I can remember, I want to say azimuth and elevation is probably the most intuitive way to tell you where the vector is pointing. But most game programmers don't even know what that means. So it's even trying to figure out what form the answer is going to be in is kind of difficult. I mean, it's going to be difficult to tell you where the vector points in any way that actually means anything significant to you. So if we were in 2D here on an XY graph, you basically have 4 quadrants that the graph could be broken up into, like positive, positive, and negative, negative, and positive, negative, and negative, positive. 4 quadrants. I don't know what you call that in 3D. I'm going to call them quadrants here for lack of a better word, but you'd have basically 8 of them in 3D. And you can kind of look at the numbers in the vector to see where the head of the vector is positionally, which quadrant it is in, and that will give you a vague idea of which direction it points in. And the vast majority of the time, that is sufficient to know where the vector's pointing. It's rare that you even need to know that. But if you're trying to debug or something, and you want to have some vague idea of where the vector's pointing, you can kind of look at what quadrant it's in and have a vague idea. The way you use these vectors is that you can start out with a known direction, like pointing straight down the z-axis. I mean, if let's see, x, y, z is the last value, so 0, 0, 1 is going to point straight down the z-axis. And so I know exactly where that vector is, or where it's pointing to at that point, starting out. And I can use that as a starting reference, starting position, to always know that we're pointing in the direction that makes sense. And then if I rotate the vector, now I know where I'm rotating from. And from that point forward, I don't really need to know where the vector points. I can rotate it by 90 degrees around the y-axis and know that it's pointing in the correct direction, because I know where it started and I know it was supposed to rotate 90 degrees. Wherever it's pointing now, it's pointing correct, as long as the math was done correct. So for a starting point, you may want to start the vector pointing in a direction that you know what direction it is along one axis, and then move and rotate it from there as needed. And then you can trust that it's going to be pointed in the correct direction. Generally, you set the initial direction of the vector along a known axis, rotate it to where you want it to be, and then use the vector rather than trying to figure out which direction it points in. If I'm using the vector to tell an object where to go, I as the programmer do not need to know where that is, as long as the object goes wherever that vector tells it to. Let the vector do the work for you. That's what it's for. Don't micromanage it. Don't try to control every little aspect of it. It stores what it's supposed to store. It does the math correctly. Let it get its work done and leave it alone. Okay, so controlling where vectors point. How do you rotate the vector? We talked about having a known starting direction, and that we're going to rotate it, but how do you actually do that? Well, you do it with this formula that's written in black here. final x equals cosine of the rotation angle times the original x position minus the sine of the rotation angle times the original y position, and the final y position equals the cosine of the rotation angle times the original y position plus the sine of the rotation angle times the original x position. That is the rotation formula. Notice that the angle here I've written with the Greek letter theta. It's the same in all four places. It's the exact same angle. You get the cosine or the sine depending on what you need, but it's the same angle in all four cases. And in both formulas, the original x is the original. It's the same original x. The original y is the same original y. But you have two x values. You've got the original x value and you've got the final x value. In other words, the x value of the starting position and the x value of the end position. And you have two separate formulas, one for the x value and one for the y value, because we're working in 2D here. We're working in two dimensions here, and it requires two formulas, because when you're rotating, the new x position is not only affected by or it's not only going to affect the new x position, the original x position is going to affect both the x and y position in the final. This formula is really difficult to prove. When I first saw it, it was pretty obvious that it works, but it drove me crazy as to why it works. And for a long time it drove me crazy until I decided I was going to figure it out and figure out why it works. And I would strongly recommend that you don't do that. I took, I think, about a full week to write a mathematical proof that proves this formula and proves that it is a universal truth. And basically, I found this formula in the back of my college trig book, in order to prove it, I basically had to go backwards through the entire college trig book and use everything that was taught in that trig book all the way back to the beginning in order to prove this one formula. In order to prove it, you basically have to know all of trigonometry. It takes pretty much everything you learn in trigonometry to prove this formula. So if you really are bound and determined to prove it, you need to go take a trig class. You may already have trig, and I may be explaining what you already know, but I'm trying to gear this video and this whole series to people who hopefully know algebra but haven't had any exposure to trig necessarily. And you don't necessarily have to know trig for this. Even if you're programming this formula in, there's a cosine function in your API, there's a sine function, and as long as you know how to use them properly, you don't necessarily have to know what cosine or sine actually means. Yeah, if you really wanted to prove this or understand how it truly works, you really need to become an expert in trigonometry, because it pretty much takes a full, complete understanding of trigonometry in order to understand how this works and why it works. Just kind of accept it does work. It actually, it works. Try it. You'll see it works. And it's not only for rotating vectors, but taking any position in 2D and rotating it will use this formula. In fact, we're going to see that even doing rotations in 3D use this exact same formula. Just understand it works and live with that. I mean, you may be like me and not be able to rest until you kind of figure out why it works, but it's ugly unless you already really know trigonometry really well, and then I probably won't need to be explaining this to you anyway. So if we actually plug in some values, let's say we've got this vector 4, -2, and we want to rotate it 127 degrees. Well, generally in your API or whatever, it's going to want this done in radians, which are a different unit of angular measurement. You can fairly easily convert degrees to radians. Most APIs, pretty much all of them, will have some sort of method or function or something that will convert degrees to radians for you, so you don't even really necessarily know how to do the math. The math is actually pretty simple if you know how to do it. So here I've converted 127 degrees to 2.21 radians, basically. I'm rounding here to make space on the page and just to keep things simple, so don't be surprised if there's some rounding errors and whatnot. But basically we plug in that value in radians 2.21 into all four places in both formulas. Then we calculate the sine and the cosine of that angle and plug that value into the formula, and then it becomes just simple multiplication and addition and subtraction and whatnot, and we reduce it, and we eventually get the final x value of negative 0.809 whatever, and y equals 4.39 blah blah blah. I wasn't extremely rigorous in my math here, and there might be some rounding errors since I did some pretty significant rounding. But we basically get a new position of negative 0.8, 4.4, and that should be 127 degrees away from the original position, rotated around the origin. And notice that we're always rotating around the origin. This works not only for vectors but any position. The rotation formula isn't specific to vectors. It's just that it'll rotate any 2D position here, and the head of our vector is a 2D position. So we can rotate that 2D position by whatever angle and calculate the result 2D position, which will be the new position of the new vector, or the position of its head, and use this to basically calculate a rotated vector. So what about the 3D rotation formula? How do you rotate a 3D vector? Now that we've seen how you rotate a 2D vector, we're going to be working in 3D. How do you do that? That was it. There's no such thing. Basically, you have looked at the way, and we have perfectly described how to rotate 3D vectors, because you can't. There is no such thing as a 3D rotation formula. What there is the 2D rotation formula. And basically we reduced the problem to a 2D rotation. If you look at this drawing, if we take our 3D vector here and we want to rotate it around the negative, or around the z-axis, negative or positive, the z-axis, basically if you rotate this around the z-axis, the z position will not change. The z coordinate of the vector head's position is going to remain the same as long as you're rotating around the z-axis. So we can basically say our final z is equal to our original z. And then we can use the 2D rotation formula to rotate the x and the y part of it, because the z isn't affected. And so it basically gets turned into a 2D problem. You could basically imagine the rotation happening on the xy plane around the z-axis. And if you imagine the shadow of this vector as it rotates, you could rotate that shadow, and then that would give you the correct x and y coordinates of the new position, and then the z position would be the same as it originally was. So the 2D formula works here, even though we're rotating in 3D space, as long as we're rotating around this one axis. It's the exact same formula, x, y. We're just adding a z and saying the z doesn't change. And this formula works. It works in 3D. This is the way you do a 3D rotation, is you rotate around the z-axis. To rotate objects in 3D space, you have no choice but to rotate them in 2D on one plane at a time. If you ignore the z dimension, you can do a 2D rotation on the xy plane. This will give you a three-dimensional rotation about the z-axis. The problem here is that you might occasionally want to do a rotation that is not around the z-axis. By itself, this is not a lot of help because you're only able to rotate around one axis. However, if you flip to another axis, you can basically rearrange the same formula to work on all three axes. Basically here, if we're going to rotate around the x-axis, you can say the final x value will be the same as the original x value, and basically switch out z every place that you had x before, in both the final y and the final z formulas. And basically now you're casting a shadow onto the zy plane and rotating around x, and basically doing a 2D rotation in 3D space in order to figure out the final position for the rotated 3D position, or the rotated 3D vector. You basically change the axis you rotate on by switching out the x, y, and z values. To rotate on the x-axis, you rotate in 2D on the yz plane. Z acts as the x-axis, making x the rotation axis. And so, to be complete, we need one more rotation around the y-axis in order to be able to rotate on all three axes. And once you can rotate on all three axes, you can rotate into any position. So this is enough. This is all we need to do 3D rotations. So all of your 3D rotations are actually done in 2D on three separate axes. And the math works the same here. The final y is going to be equal to the original y, and then we switch out all the z values where there had been y values on the 2D formula, and it works exactly the same. So by doing 3D rotations, you can rotate into any 3D position. Due to gimbal lock and similar problems, you may be better off loading a transformation matrix with a set of rotations and then apply the one transformation matrix to the vector. Basically, you don't need to know about this. We haven't covered gimbal lock, we haven't covered matrices. I'm just kind of giving you a preview of where we're going and how this is used in the real world. Rotation matrices use the same rotation formula under the hood. So when we get into matrices and we get into using a matrix to do a rotation, understand that that matrix contains the 2D rotation formula. Internally, the matrix holds the same 2D rotation formula we just looked at. The matrices use the same method to do the rotation. Even though they're 3D matrices and they're doing 3D rotations, they're actually using the 2D rotation formula just as we just described to do those 3D rotations. And that's really how matrix rotations work. We'll get into that later and eventually get into gimbal lock. In the gimbal lock video, we'll cover the problems with rotations that occur in a lot more detail. So you load the matrix with rotations, then you multiply it times the vector. Often there's a method in any given environment to do this for you. So when you're using a matrix to do a rotation, you'll have your vector, and you can basically just multiply the vector times the rotation matrix, and the results, it'll return a vector as a result, and the returned vector will be the rotated vector. Below at the bottom, it shows kind of an example of this from DX11. This is kind of pseudocode here, where XM vector is a 3D vector, and you have actually two methods here: the XM vector 3 transform and the XM matrix rotation roll pitch yaw. And I've actually nested basically one function inside the other, which you do a lot in C++, because the XM matrix rotation roll pitch yaw method will take a pitch, a yaw, and a roll as input and return a matrix. So if you're not familiar with pitch, yaw, and roll, basically pitch is rotation around the x-axis, yaw is rotation around the y-axis, and roll is rotation around the z-axis. And you can give the angles there in radians for pitch, yaw, and roll, and it will return a matrix that contains that rotation. And then you can apply that rotation matrix to your vector with XM vector 3 transform, the first parameter being your vector, the second being the rotation matrix, and it will return a vector as an answer, which will be the rotated vector. And so you really didn't need to know any of the math here. All you needed to know was that in order to rotate your vector, you needed to use XM vector 3 transform to rotate your vector using a matrix. We're using a rotation matrix, and you needed to know how to build that rotation matrix with XM matrix rotation roll pitch yaw by feeding it roll yaw and pitch values. But you don't need to know this even if you're going on to do DX11. This, when you get into actual using DX11, you'll need this, but until then, you don't even need to know this. And as you can see, all the math is done here for you. You don't need to really understand the underlying math. Vector normals. So you'll hear the term normal in graphics or game programming like all the time. It's a very commonly used term. Vector normals are a vector that has had its length set to 1, and we call that a normalized vector, or normal for short. You normalize a vector by dividing the vector by its length or amount. The normalized vector, in this case, I give the position of the head of the normalized vector, still points in the same direction, but its amount or magnitude is now 1. So the direction is preserved while the amount is thrown away. You use a normal to represent a direction. It's still an arrow, and its length set to 1, which we set it to 1 because we don't care about the amount. You're saying, I care about the direction, I don't care about the amount. And so we set it to 1 to indicate that we don't care about the amount. And part of the reason we set it to 1 is because later, if you do math on it, it simplifies things to already have it normalized. When we get into setting the length of the vector, you'll see that having a normalized vector to work with makes the math a little bit more simple. The big thing here is to understand that when you normalize a vector of any length, the direction is going to remain the same. It's still going to point in the same direction. It's just going to reset its length to be 1. And here we had our vector 4, -2, -4, and when you normalize it, if I did the math correctly, it should give you a vector of 0.6, -0.3, -0.6, and I'm rounding at different spots here. I believe this is 2/3, -1/3, -2/3, and all of those are infinite numbers that go on forever and ever and ever. And so you kind of have to arbitrarily decide when to round them off and cut them off. And in the interest of getting everything on the page here and simplifying things, I rounded in a couple different ways here, but just understand that I may have some rounding errors there, but basically this is a normalized vector. And at the bottom I show how you normalize a vector. Here we're kind of introducing matrix algebra, matrix notation. We haven't got into that yet. The matrix video will get into that, how to do matrix math and everything. But just kind of think of the stuff that's in square brackets, kind of think of it as having a comma between every number. So starting on the left in the bottom left hand corner, the 4, -2, -4 is, you can think of it as 4, -2, -4. It's the position of our vector head. and we're trying to calculate its length, the length of the vector. So below we've got the magnitude or the amount of or the absolute value of the quantities 4, negative 2, and negative 4. Basically, we're trying to calculate the magnitude of the vector. We're taking our vector on top of the division and dividing that by its length at the bottom. And as we already covered, the length can be determined with the 3D Pythagorean theorem. We can take our vector, do the 3D Pythagorean theorem on it, we'll get the square root of 36, and the final answer for the length is 6. So we're basically taking the x, y, and z and dividing each of them by the length of the vector, which is 6. And that gives us basically 2/3, negative 1/3, negative 2/3. Vector normals, or just normals, are vectors that have had their length set to 1 through the process of normalization, which means when you set it to a length of 1, like we just did. We remove the length because we want to only use the normal to represent a direction. We don't care about the amount at all anymore. By setting the amount to 1, we are indicating it no longer matters to us. If you were to zero the length of the vector, it would cease to exist because it would have no amount. It would not be capable of indicating a direction. Nonetheless, you will occasionally see zeroed vectors in game programming on occasion. So basically, if you take to zero out the vector, you would take the head and move it to the origin. At that point, the head is on top of the tail infinitely. They're both at 0, 0, 0. So how do you calculate the length of the vector? What does the length of the zeroed vector even mean? What direction does it point in? It doesn't. It doesn't exist. The vector has gone away. It's a direction and an amount, and you've taken away both the direction and the amount. So there is no vector. It's a zeroed vector is the absence of a vector. There is no such thing as a zeroed vector. But they don't really treat it that way in your API. They treat a zeroed vector kind of as a real thing. There are some places where using a zeroed vector is pretty handy. So rather than treating it as completely non-existent, it treats it as kind of sort of existent. Basically, the head position still exists, which is 0, 0, 0 at that point. But if you try to calculate a direction, or especially a length and amount, you're probably going to get divided by 0. It's probably going to blow up and get pretty angry at you. So just realize that when you have a zeroed vector, you basically have the absence of a vector, the lack of a vector. You don't really actually have like a real vector at that point. And that's why if you want to represent just the direction and not the amount, you can't zero out the vector because that would lose the direction as well. So basically it's just kind of become convention that a normal, a vector that only represents a direction and not an amount, should have a length of 1. The difference between a vector with a length of 1 and a normal is nothing but how you intend to use it. If the amount of 1 is what you intend, then it's a vector. If the amount of 1 indicates you don't care about the amount, then it's a normal. So it's all in the intent. If you intend the vector to represent a direction, then it's a normal. If you don't care about the amount, it's a normal. If you care about the amount, if you intend it to represent a direction and an amount, then it's not a normal. I've seen some arguments where, they argue that it's not the same thing. It is the same thing. A normal and a vector that just happens to have a length of 1 is the exact same thing. It's a vector with the length of 1. But the way you refer to them, the way you treat them, the way you deal with them is based on intent. And it's not necessarily enforced. You could get into a bug or something where you chose the wrong thing there. But the difference between a normal vector and a vector that just happens to have a length of 1 is entirely based on what your intent is when you're using it. One of the main ways that you'll see vectors used as normals is representing directions, especially in shaders, to calculate light or lighting. You'll see them used a lot in shaders for things like determining what direction a surface faces compared to the direction the simulated light source is facing. For example, if a triangle faces directly into the light so that the light's normal and the triangle's normal are in the exact opposite directions, the triangle would be lit with 100% of the light color. As it turns as much as 90 degrees away from the direction of the light, it gets less and less percentage of amount of that light until at 90 degrees it gets 0% of the light's color and continues to get 0% at any angle greater than that. So if we look at the drawing here, we imagine the scene being lit up by the game world sun. This is generally used for outdoor lighting because indoor lighting is the position of indoor lighting is much more specific. The lighting sources are a lot smaller. When the sun lights things here, it lights up half of the entire Earth at once, simultaneously, from basically what is one direction. I mean, if you want to get real specific, you might say there's a slight angle to it, but for the most part, it all seems to come from the exact same direction. The sun is far bigger than the Earth, and all of its light basically seems to illuminate the entire half of the Earth equally. So whether you're standing in one position or whether you're standing 10 feet to the left of that or 10 feet to the right to that, the light's still going to appear to be coming from the same direction. And so this simulation works really well for outdoor lighting type situations, not so well for indoor lighting type situations. And later we'll get into this and we'll see that basically everything in the game world is drawn using triangles. And so here we have a triangle, and the black arrow represents its face normal. That's the direction that this triangle is facing. And the yellow vector represents the direction that the sun is shining in, or shining from. I've got it coming out of the center of the sun there, and but also realize that the position of vector doesn't matter. We could just as easily move that vector so its tail is on the origin, which is exactly what I did in this drawing. And you can see that it's pointing in the exact opposite direction of the face normal, which is the black vector. And so when these two vectors are pointing in exactly opposite directions, you know that the face is pointing perfectly into the light, and you can give it 100% of the light's color to illuminate it. Obviously, if it's facing away from the light, you don't want to give it any of the light's color, and so it will not be illuminated when it's facing away. When it's facing away, the black vector will actually turn to, if it's perfectly facing away, the black vector will turn to align perfectly with the yellow vector. And so when they're pointing in the exact same direction, you know it shouldn't get any of the light. May not be perfectly obvious, but if you think about it, it should be fairly obvious that getting 100% of the light means you're facing perfectly away from the lighting vector. As you rotate as much as 90 degrees, you'll get a percentage of the light. You'll get less and less light until at 90 degrees you get 0% of the light because you're no longer facing the light. And anything beyond 90 degrees you're facing away, so you wouldn't get any of the light if you're facing more than 90 degrees away from the light source. 90 degrees is perfectly perpendicular, so it's maybe a little questionable whether you should get some light or not, but generally you're going to get 0% of the light at 90 degrees. Think of it this way: if you're 89.99999999999 degrees away from the light, you're still going to get some of the light. You've got to cut it off at some point, and the cutoff point is 90 degrees in most shaders that you'll find, I think. But between 90 degrees and 0 degrees, 0 degrees being pointing perfectly into the light, between that angle, you'll get a percentage of the way between the two. In other words, if you're 30% between 0 and 90 degrees, you'll get 30% of the light. If you're, or actually it's going to be the inverse of that, right? Because the closer you get to 90, the closer you get to zero light, and the closer you get to 0 degrees, the closer you get to 100% light. So it's kind of backwards there. You got to flip it. So if you're 30 degrees away from the light, you should get 70% of the light. Anyway, that's basically how you use normals in like a blend Phong shader, for example. Some of your basic shaders will do this. They'll basically have normals, and this is how you're calculating your lighting and how you actually use normals in 3D game programming. Vector scalar multiplication, setting a vector's length. You can multiply vectors times regular numbers. Regular numbers are what we call scalars. When you multiply a vector times a scalar, it takes that one number and multiplies it by every dimension in the vector. So it multiplies by x, y, and z. If the vector has a length of 1, this will make the vector length or amount the same as the scalar number. So if you got some vector and you multiply it by a regular number, which we call a scalar, that's going to, whatever the length of the original vector is, that's going to multiply its length times that scalar number. So if we have a vector and it's got a length of 6 and we multiply it by the number 3, which is just a regular number, the vector times 3 is going to give us a vector that has a length of 18. And it does this because it multiplies each dimension by that number. Now, one very common trick, one of the ways you'll see normals used a lot is that if you normalize a vector and set its length to 1, then it will take on whatever length the scalar has. So if you take a normalized vector and multiply it times 7.4, its length will become 7.4. So you can set the length of any vector by multiplying it times, or by normalizing it first, and then multiplying times the length that you want it to be. So if you got, and the key point here is that the vector continues to point in the same direction as it did before. You're not changing the direction the vector points, you're only changing its amount or its length that it stores. So this is extremely handy because if you want to change a vector's length, you can set it to be whatever you want it to be very easily. If you want it to be 2.35 in length, you could take any vector and normalize it and multiply it times 2.35, and wherever it points, it will have a length of 2.35. And so you have perfect control over the length of the vector because you can set it. First of all, you know how to calculate its length to find out what its length is anytime you need to know what it is, and you know how to set it to be whatever you want it to be. So to set a vector to a specific length, such as 7, multiply it by that number. Multiplying a normalized vector times 7 will give you a vector that continues to point in the exact same direction but has a length of 7. This is one of the reasons that normalizing vectors is so handy. If you have a vector with a length of 12 and you want to change its length to 5.36, just normalize it and then multiply it by 5.36. And in the drawing I've got the original vector as a dotted line, black arrow, and the normalized vector pretending that it has a length of 1. Since I don't have any tick marks are here to actually designate units, that's our normalized vector with a length of 1. Vector addition. So let's go back to 2D for a moment to look at vector addition, because it'll be maybe a little bit easier to understand if we first start looking at it in 2D. If you take a math course that has vectors in it, they're probably going to start working in 2D, certainly in high school or something like that. Looking at vector addition is probably just easier if you look at it initially in 2D. So often it's helpful to think of vector addition as happening away from the origin. I said these vectors don't really have position and the tails are always at the origin, but and when you're doing vector addition, it's probably easier to, addition and subtraction, it's probably easier to imagine the vector as being not positioned with its tail at the origin, but rather to have its tail positioned at the head of the vector you're adding it to. And for vector subtraction, you have basically the same thing. And for vector cross products, you'll also, if you're calculating a face normal, you'll probably imagine the vector being in the center of the face, even though technically that's not where it's really at. So you can kind of, since the position's irrelevant, it doesn't matter, you can kind of imagine them being positioned wherever you want, as long as the direction remains the same and the length of the vector remains the same. In math class, they teach you to place the tail of the second vector in blue to the head of the first vector in red. The result is a vector that points directly to the head of the resulting vector. Our result vector is yellow, but vectors are not dependent on position. The yellow result vector is a vector between the original red vector and the vector being added to it, which I've moved to put its tail back at the origin. Notice the blue dotted vector is exactly the same direction and amount as the solid blue vector. I literally copied, pasted, slid it over, and then changed its property to be dotted. But if we're taking the red vector and we want to add the blue vector to it, you can imagine it having its tail positioned at the head of the red vector. The yellow vector is going to be the answer. That's going to be your result. That's the answer that you get back is the yellow vector. You'll get the position of the head of the yellow vector. And when you position the blue vector, the solid blue vector this way, it will point right at the exact position where the vector addition, or right, it'll point exactly at the tip of the yellow vector. In actuality, when we do the math, the solid blue vector gets moved to have its tail at the origin, which becomes the dotted blue vector, and adding the red vector, the solid red vector, to the dotted blue vector will give you the yellow vector as an answer, because the positions don't matter. It's the same answer wherever the blue vector is positioned. The dotted red vector is the same as the original solid red vector, and you can see that points to the answer vector, the yellow vector, as well. You can work through the geometry here, but the dotted blue vector is the same vector and will produce the same result vector. If the dotted blue vector is negative 0.5, 5, then adding negative 1.5, negative 3 to that gives negative 2, 2. So the first one, negative 0.5, 5, is the blue vector, right? Yeah, that's the dotted blue vector. That's the position of the dotted blue vector's head is negative 0.5, 5, and our red vector has its head at negative 1.5, negative 3. So in the bottom left, we got some more matrix algebra here. You don't really need to know how to do this, but you can basically imagine the things in brackets being separated by commas. Negative 1.5, negative 3. The first one is basically the red vector, or the position of its head, plus negative 0.5, 5 is the position of the dotted blue vector's head. You add those two vectors together. Basically, you're adding their x values and y values. X is in blue and y is in black. You're basically just adding those values together, and that will give you negative 2, 2, which is the position of the yellow vector's head. Basically, this is how you would solve this problem. If you were using the solid blue vector, you would essentially, then you have two positions, and then you've got to calculate both the head and the tail, and it would still give you the same results. Basically, to simplify it, you basically need to move it to the origin by subtracting the tail position from both the head and the tail, and then your vector will at that point be the dotted blue vector. So what is vector addition good for? We often use vectors to represent movement that starts with a position. I've stressed that the position of a vector is irrelevant, largely to point out an inconsistency in the way we use them. We often use them to represent positions. All vectors have two positions. Not all positions are vectors. So we do use positions as vectors because a vector object, a vector class in your framework, API, whatever, it's going to be a position. It's actually two positions, but the second position we don't store. The second position is always at the origin, and there's no point in storing it. It saves a tremendous amount of space, memory space, and processing power and everything, because we're cutting the storage size of the vector in half by not storing half of it, because we know that the tail is always at the origin, and that doesn't harm anything. That actually makes things more simple and simplifies things and makes the math easier. There's no reason not to do that, and every reason to do that. And but it doesn't change the fact that a vector is actually two positions, the origin plus the position of the arrowhead. And since that means you only store one position, it's very natural to put a position into a vector. But you got to remember the mantra: a vector is nothing except an amount tied to a direction. And there's no position on that. It doesn't matter. In that statement, it doesn't matter where the vector is positioned, and it's not a position. The positions in a vector are only relevant to one another. But when you store a position in a vector as opposed to the position of a vector, the position, amount, and direction doesn't matter. Storing positions in vectors makes them easy to do vector addition on. Technically, a position has a direction from the origin to the position and an amount of that distance, although no one usually cares about that, which is why it's not really a vector. So yeah, I mean, if you throw a 3D position into a vector, technically it is a vector, which is why there's a little bit of argument about it. But if it's the position of an object in 3D space, technically the vector is an arrow that points from the origin to the 3D position and has an amount or length of the distance between the origin and the position. But the thing that makes it not a vector is that you don't care about that. Nobody cares about that. Nobody cares what direction it is from the origin to the 3D position, and nobody cares about the amount of offset from the origin. Technically that is what it is at that point. That it technically is a vector, but you're not using it that way. You don't care about that. So in reality, it's not really a vector, even though we've shoved this position in our vector object in our 3D API. I want to make a distinction about that, because when you first start getting into vector programming, you'll see positions stored in vectors all the time, and I want to make it very clear that that's not really a vector. And because if you don't understand that, then it's just really easy to get confused about what is a vector and what is not a vector, and this whole vector thing doesn't make any sense because we're not being consistent in the way we use it, and it just adds a lot of confusion, and I don't want you to be confused at this point. So that's why I've stressed so many times that position is irrelevant, and that vectors have nothing to do with position, and that a vector is actually two positions, not one position. But we'll see here in a minute that it becomes very handy to throw a position into a vector, and then you can do vector math on it, and then it kind of makes sense. But just understand, when you store a position in a vector, that doesn't necessarily really make it a vector. It's just we're doing that to simplify the math and be able to do vector math on it. Still, we normally put the positions of things from vertices to entire game objects into vectors all the time. Yeah, we use positions in vectors a lot. We often use vectors to move the position of objects. Here we have the red vector pointing to our starting position. The solid blue vector represents our desired movement, direction, and amount, which that vector is -1, 1, 3.5. The dotted blue vector is the same as the solid one. Again, I copied and pasted it. It points in the same direction. It has the exact same length because I copied and pasted it. The result vector is the yellow vector, which points to the final position caused by the movement. The result vector contains the new position caused by the movement. Notice that you don't need to know what the original position was, where exactly the movement vector pointed, or how long it was in order for it to work. Just add the vectors together and store the results, and it works. So going back over that, we've got our red vector, and we want to add the blue vector to the red vector. Basically, the red vector represents our starting position, the yellow vector represents our ending position, and the blue vector represents our movement, probably movement per frame. And the blue vector points in the direction we want to move in. In 3D space, notice that this vector could point anywhere. So we're not moving straight down the axis. You do that a lot in 2D game programming where you move straight across the axis or axis aligned. You can use 2D vectors to not move or move at angles that aren't axis aligned. In 3D movement, you're probably always going to want to move at angles that are not axis aligned. We can point this vector in any 3D direction we want it to be pointed in, and that's what direction we're going to move in. And the amount is the amount during this frame, or the distance during this frame that we're going to move. So we can control our movement by controlling the blue vector. Our blue vector becomes our movement vector, and we can set that movement vector to point whatever direction we want the movement to occur in, and set its length to the distance we want to move during that operation or during that frame. And when we add, or when we put our original position in a vector, the red vector, and we add the blue movement vector to it, the result vector, the yellow vector, is going to point right at our resulting position as a result of that movement. And so it makes it real easy to do 3D movement this way. And when we get into physics, we'll be doing the same thing, except for we'll get more complex. Maybe just to kind of give you a little bit of a feeling for that, the blue vector might become a velocity or speed vector. It's still a movement vector, but it's a movement that occurs every frame until we tell it to change size or stop, and we can speed up and slow down by changing the length of the vector. Or you can do velocity, which is speed, in addition to acceleration, where we use another vector, the acceleration vector, to speed up and slow down or change the blue vector. One vector changes the blue vector, and then the blue vector is a movement vector that gets added to one position to give us the next position. It just kind of gets more and more complex from here, but this is the foundation. This is the start, where basically you've got one position, you apply a movement vector to it, it'll give you the next position. And in the bottom left, again, we have kind of a matrix algebra form of adding two vectors together. I've got the x, y, and z coded in blue, black, and green. And we're basically adding the two x values, adding the two y values, adding the two z values together to give us a result vector, -2.5, 0.5, 2. Vector subtraction. Vector subtraction basically works the exact same way, just opposite, just backwards. In game programming, it's mostly used to determine the direction and distance from one position to another. If we had a position stored in our red vector and another position stored in our yellow vector, and we wanted to know the direction and distance or amount from the red vector position to the yellow vector position, we could subtract the red vector from the yellow vector, order determines direction. The order that you do the subtraction in actually matters when you're talking about vectors. The order pretty much of all these mathematical operations will matter when you're talking about vectors. So looking at our drawing, for vector subtraction, say we've got two vectors. We have two positions, the red vector position and the yellow vector position. This is basically deconstructing what we just did in vector addition. I think I'm actually using the exact same vectors here. But the way you might actually use this is, say you have a position of two objects in the 3D game world, and your object is, say the player object is it's at the position in the red vector, and the game object that you want to look towards and know the distance to is at the position pointed to by the yellow vector. And so if you take the yellow vector and subtract the red vector, it will give you a result vector, which is the solid blue vector, that will have the direction from our position to the other game object's position, and the length of that vector will be the distance from the player object to the game object. So you can calculate an exact direction to look in to go from one object to another in 3D space. I mean, you're not just talking about a 2D direction here. You're talking about a 3D direction that not only can point in any of 360 degrees, but you're talking about a 360 degree sphere, not a 360 degree circle, and know the exact distance between the two objects with that one vector. You can imagine it as being the dotted blue vector because the position is irrelevant. The position doesn't matter. And so you can kind of imagine it pointing from the red vector to the yellow vector. When you position it at the head, it makes that kind of more obvious to see, but it's pointing in the same direction and it has the same length regardless of whether it's positioned at the origin or not. And so even when it's not positioned at the origin, it does contain the correct direction and the correct length. And then you may want to do like vector addition to move the player object to the game object. If you did the vector subtraction to calculate the distance and direction from the player object to the game object, and then you took that vector and added it to the player vector, it would move the player vector to the object, or move the player to the object, move the two positions together. At the bottom, you've got kind of the matrix algebra form of the math here. And again, X, Y, and Z are color-coded here. And you can see that we're adding X's together, or subtracting X's from one another, and subtracting Y's and subtracting Z's, which gives us the yellow. Is it the yellow vector? I'm losing track here. The blue vector, right? It gives us the blue vector of... but regardless, this is the way you do vector subtraction. You take one vector and subtract it from the other, and the result vector should be the direction and distance between the two positions. And here we started out with the yellow vector and subtracted the red vector, and this gave us a vector that points from the red vector to the yellow vector. If you switch the order, if you do the red vector minus the yellow vector, then the direction of the blue vector would change. It would be exactly the opposite. It would point in exactly the opposite direction. In other words, it would then point from the yellow vector to the red vector. Vector multiplication. What does it mean to multiply two vectors together? How do you multiply two arrows? What does the result of that even mean? How do you multiply an elephant times a giraffe, an apple times an orange, a sound times a color? You don't. That's how you do it. Vector multiplication only has what meaning we give it, just like multiplying apples times oranges can only mean something if we set specific rules about it, what it actually means, and then it can mean pretty much anything we want. If you think about it, that's basically how all mathematical operators like addition, subtraction, multiplication, and division work, even with regular numbers. It's just that we all know the rules of working with numbers so well that we just assume everyone knows what it means to multiply two numbers together. Vector multiplication has a completely different meaning than multiplying numbers together. There are two types of vector multiplication: vector cross products and vector dot products. So vector multiplication tends to blow people's minds and cause people to drop out of trigonometry class and never approach mathematics or game programming ever again. It's not really that scary. It's not really that bad. But the first key is to know that there really is no such thing as multiplying two arrows together. If you look at that and go, how can that even mean anything? That's not a real thing. You're right. It's not really a real thing. But we can basically agree upon some rules and make it a real thing by, saying this is what it means when you multiply two vectors together. And we have two different types of vector multiplication. We have the vector cross product and the vector dot product. So let's look at the vector cross product. Vector cross products are used to define a 2D plane in 3D space and determine what direction that plane faces. So in the drawing here, we got this gray 2D plane. We've got two vectors, the red vector and the blue vector. And the red vector and blue vector live on this same 2D plane here. That's how we are defining the 2D plane. The 2D plane is whatever plane it is that you would need in order to make the red vector and the blue vector live on the same plane. And the vector cross product is going to give us the yellow vector, which theoretically should point straight out of our 2D plane. It should tell us what direction the 2D plane faces. And so where you see this in game programming a lot is that everything in the computer graphics world is drawn with triangles, everything. And for lighting and other purposes, you're going to need to know what direction that triangle faces. Well, you can take two sides of a triangle, since they're connected, assuming that their position in 3D space doesn't matter, because like in our lighting example earlier, basically the light source is just a direction, and the direction doesn't change when you move in one direction or the other. It's really your angle that determines the lighting. So position's irrelevant. All that really matters is the angle. So you can imagine this triangle having its tip move to the origin, and then it's pretty easy to see that the two sides touching the origin of the triangle are basically two 3D vectors. No matter how this triangle is oriented in 3D space, the third side of the triangle would actually be vector subtraction between the two vectors, the two sides that you have. Would be one way you could calculate it, but you really don't need that, because all you need is the two vectors of the two sides to calculate the cross product, and then it will tell you what direction that triangle faces, or what direction the plane that triangle is on faces. Then you can normalize that vector from there if you need to. But here I'm showing that that the order that you apply the cross product in matters. If you do the blue vector cross product red vector, it's the exact opposite of doing red vector cross product blue vector, and then you'll get the if you apply it in the reverse order, you'll get the orange vector, which supposedly points exactly opposite of where the yellow vector points. Or you're basically looking at the other side of the plane and saying, what direction does that side of the plane face? So at the bottom here, kind of done the matrix algebra to show how to calculate the cross product with the x, y, and z color coded here. And you're kind of cross applying or cross multiplying the two by one another, and then subtracting the two result sets. basically this is how you calculate a cross product, but any API or framework that you work in is going to know how to do this for you. You just basically say, I need the cross product of these two vectors, and it will return the result. And you just kind of need to know that the result gives you a vector that points directly out of that plane, and that reversing the order that you applied the two vectors in will reverse the order of the vector. And that's pretty much how you're going to see vector cross products used in 3D graphics programming in probably almost every case. Vector dot products, also known as the inner product. These are used for matrix multiplication. When we get into matrix multiplication, you'll see that the vector dot product is used for vector multiplication. At the bottom here, I show kind of matrix algebra form of how to do a vector dot product with two vectors. Before we use the X symbol for multiplication or cross product. Here we use the dot symbol for the multiplication dot product of these two vectors. And the answer here, you can see, is not a vector. It's not 3D at all. It's actually 1D. It's reduced to a 1D value, -4. Probably the easiest way to think of dot products is, in this example, the dot product projects a shadow of one vector onto another. Easiest way to see this is if you take an a vector that's pointed down one of the axes. In this case, 1, 0, 0 is pointed straight down the x-axis. It's a normalized vector, and you dot product that together with this vector, which happens to be 4, 3.5, 0. It'll return an answer of 4. And if you were to take the x-axis vector, the x-axis normal, and multiply it times the scalar 4, it would lengthen it so that it basically comes to the point on the x-axis where that dotted line is at. And its length would be 4 at that point. And if you imagine a light shining down the y-axis from above, it would turn the blue vector into a shadow on the x-axis that would be exactly the same as that x-axis vector of 4 length. So basically you're kind of mathematically casting a shadow of a vector onto an axis. If you were to normalize the original vector, which in this case is already a normal, and then multiply it times the dot product, you get a vector the length of the shadow of the second vector, which or the shadow of the blue vector. The dot product can be used to calculate the angle between two vectors. So another way to use this is if you want to know the angle between two vectors in 3D space, you can imagine them existing on the same plane, the same 2D plane in 3D space, and you can get the angle on that plane, on that 2D plane, between the two vectors by using the dot product. The angle between the vectors is the arc cosine of the dot product of the two vectors divided by the magnitude multiplied by one another. Okay, so that's written out as a formula right below that. The angle between the two vectors, or theta here, equals cosine -1, which is the arc cosine, of the quantity A dot product B divided by the magnitude of the two vectors. And use the 3D Pythagorean theorem to get the magnitude or amount of vector A, and then use the 3D Pythagorean theorem to get the amount of vector B, and then multiply those two results together and take the dot product of the two vectors and divide by that result. And then you take the arc cosine of that, and it will give you the angle between the two vectors on that plane. Up above, you can see that I calculated the dot product as being -4. Over in the bottom left, you can see I've plugged in the values. So we have the dot product as -4, and then you've got the length of the two vectors. We calculated the first vector, its length, earlier and got 6, and then I run a quick calculation. I think the blue vector has a length of 5.46. Take the absolute values of those and multiply them together and use that. -4 divided by that, and then take the arc cosine of that, plug it into a calculator. You should get something like 1.693 radians, and then if you convert radians to degrees, it comes out supposedly 97 degrees. I may have not got my math all perfectly correct here. More want you to kind of just get a vague idea of the process and see how it's done, rather than truly understand the math here, because in almost every framework out there, you just say, give me the dot product vector A and vector B, and it will give you the result back in radians. But notice that if you normalize both vectors, their length of 1 will be a divide by 1 and can be eliminated, so that the formula becomes a lot more simple. You can get rid of that whole bottom half of the formula with the magnitude if you normalize the vectors, which sets their magnitude to 1. If both vectors are normalized, then the length of those vectors is obviously 1. The absolute value of them is 1, and 1 times 1 is 1. So then you get a dot b divided by 1. Anything divided by 1 remains the same. So 7.3 divided by 1 is 7.3. Negative 23.6 divided by 1 is negative 23.6. So you can basically just get rid of the divide by 1, and at that point you have the arc cosine of the vector dot product of the two vectors equals the angle in radians. So it becomes much more simple if you'll just simply normalize the two vectors before you start. To summarize all this, vectors are nothing but an amount permanently tied to a direction. Think of them as arrows. Normalizing a vector sets its length to 1, which is basically throwing away the amount while keeping the vector pointed in the same direction. Multiplying a vector times a scalar will multiply the length of the vector times the scalar. If the vector starts out normalized in the first place, the length of the result vector will be the same as the scalar value that you multiplied it by. Normalized vectors represent directions when we don't care about the amount. If you have a normalized vector, you're basically saying, I don't care what the amount is, I've set it to 1 because I don't care. Vectors can be rotated using the 2D rotation formula. For 3D vectors, they can only be rotated around one axis in 2D at a time. There is no such thing as a 3D rotation formula. You have to use the 2D rotation formula and apply it to each axis. All of this allows you to control where the vector points and its length. At that point, you should have pretty much complete control over the vector. You know how to start it out at a known direction, set its length to whatever you want it to be, and rotate it into whatever position you want it to be. And so you pretty much have complete control over your vectors at that point. Vector addition is often applied to positions in order to move those positions in a specific direction and amount, while allowing that direction and amount to point anywhere by any amount. Vector subtraction is the opposite process and is usually used to determine the direction and a distance between two positions by returning a vector that points from one position to the other and with a length of the distance between them. Reversing the order of subtraction will reverse the order of the result vector, or reverse the direction of the result vector. Vector cross products can take two vectors that are considered to be on the same 3D plane and give a result vector that points perpendicular out of that plane and thus tells us what direction the plane faces. And again, if you reverse the order, you'll reverse the direction of the result vector. But you can basically calculate what direction a plane or a 3D triangle that lies on that plane faces using the vector cross product. Vector dot products can project one vector onto another. So you can basically project a 3D vector into 2D space for various things that that's useful for. Collision detection is the first thing that comes to mind. The calculations for doing axis aligned bounding boxes where you're doing 3D collision using boxes, uses the vector dot product to basically project shadows that you use for calculations and so on and so forth. But that's way outside the scope of this video. And that's basically everything you need to know to get started in 3D game programming and actually go extremely deep into 3D game programming. I can't think of any other use for 3D vectors that I haven't covered here. I mean, this is pretty much it. If you understand everything in the summary here, you've pretty much completely understood vectors as they are used in 3D game programming, regardless of whether it's OpenGL or DirectX or Unity or anything else.